Subspaces and quotient spaces are discussed in this video. First, we have the definition of a subspace of a vector space. If V is a vector space over a field F, then a non-empty subset W of V is called a subspace of V. If under the operations defined on V, W itself forms a vector space over F. Equivalently, if V is a vector space over a field F, then a non-empty subset W of V is a subspace of V if and only if W is closed with respect to vector addition and scalar multiplication of V. In symbols, we have W to be a subspace of V if W1, W2 are in W and alpha, beta are in F. These two together imply that alpha W1 plus beta W2 belongs to W. Now, few examples. Singleton 0 and V are subspaces of any vector space V, and they are called the trivial subspaces of V. Now, in the case of R3, if we consider W to be the subcollection of R3 as the set of all ordered triplets with the first component A and the second and third components at 0, then W is the subspace of R3 for the reason that W contains definitely the origin, so W is non-empty, and if we consider two elements A U and V given by U is the ordered triplet with first component A, the rest 0, and B to be again ordered a triplet with the first component B, the rest 0, and alpha beta are from capital R, that is the field of real numbers, then alpha U plus beta V using the coordinate y, scalar multiplication and addition, we see that alpha U plus beta V is given by the ordered triplet with the first component alpha A plus beta B, and the rest of 0 is obviously a member of W, and therefore W is a subspace of R3. Now R2, when we consider singleton 0, that is the vector with components 0 and 0, first and second component, that is it is an ordered pair, then this 0 0 is a subspace, singleton 0 0 is a subspace of R2. Then lines through the origin are all subspaces of R2, and R2 itself is a subspace of R2. So these are the subspaces, only subspaces of R2. On the other hand, if we consider W prime, so which is the collection of all ordered pairs satisfying the condition x plus y equal to 1, then we see that if you consider 1 0 and 0 1, these are two members of W prime, but when we add them up we get 1 1, ordered pair 1 1. Obviously it's not a member of W prime. The reason is 1 plus 1, when we add the components we should get 1 again, but we get 2. So the addition of these two vectors which are present in W prime, the sum of these two vectors is again not a member of W prime, and therefore W prime is not a subspace of R2. Now in the case of R3, again 0 vector, that is the vector with component 0 0 0 is a subspace. Lines through the origin are all subspaces, and then we have that is the W given by the equation x by L equal to y by m equal to z by n, and then we have planes through the origin also to be subspace of R3, and R3 itself to be a subspace. So these are the only subspaces of R3. Now again, on the other hand, if we consider W prime to be the collection of all ordered triplets with coordinates, first coordinate x, second coordinate anything, it can be x, y, but the third component is 2. Then if we consider this collection, then W prime is not a subspace of R3, as if you consider two elements, a ordered triplet x, y, 2, and another ordered triplet x prime, y prime, 2, then when we add them up we get the vector with the first component x plus x prime, second component y plus y prime, third one is 4, it is not 2. Only if it is 2 it will be a member of W prime. So W prime is not a subspace of R3. So next we have a few obvious subspaces in any vector space V, they are the intersection of two subspaces of a vector space and the sum of two subspaces. So we first prove that the intersection of two subspaces of a vector space V is a subspace of V. Let A and B be two subspaces of a vector space V over a field F. Then as 0 belongs to A and B, 0 will belong to A intersection B as well. And hence A intersection B is a non-empty subset of V. Now we consider two elements, A U and B, in A intersection B. And of course we consider alpha beta in F. Then as U and V are members of A as well as members of B, and A and B are subspaces of V, we have alpha U plus beta V belonging to A, and in the same way alpha U plus beta V belonging to B. So it has to be a member of A intersection B, and therefore A intersection B is a subspace of V. Now in the case of A plus B, we first notice that A plus B is the collection of all elements of the form small a plus small b, where small a range over capital A and small b range over capital B. Now since 0, which we can write as 0 plus 0, and 0 is a member of capital A, 0 is also a member of capital B, we see that A plus B is a non-empty subset of V. Now we consider two elements U and V as U is equal to A1 plus B1 and V is equal to A2 plus B2, where A1 and A2 are members of A and B1 and B2 are members of B. So if we consider alpha U plus beta V, then we get that as alpha into A1 plus B1 plus beta into A2 plus B2. Now by the condition in the definition of a vector space, we have this to be alpha A1 plus beta A2 and this one to be alpha B1 plus beta B2. So this is again a member of A plus B, for the reason that the first one is a member of A as A is a subspace, and the second one is a member of B as B is a subspace. So we have A plus B to be a subspace of B. Now we see that the union of two subspaces of a vector space need not be a subspace. For example, if you consider A to be the subspace what we had previously under the examples of subspace, if you consider A to be that, then another subspace with the first component 0 and the third component 0, but the middle one we have that to be any non-zero member. Of course 0 will be present, so we have B to be this collection. Then we can, as before, we can show that this B is a subspace. So A and B are subspaces of R3. Now we will consider two elements, one from A, another from B. So when we add these two members, so they are members of A union B. When we add them up, we get order triplet with entries with components 1, 1, 0. It is not a member of A union B, obviously, and therefore A union B is not a subspace of R3. So union of two subspaces of a vector space need not be a subspace. It can be a subspace provided one is contained in the other. Next we have the concept of quotient space. If W is a subspace of V, and on V if we define a relation V is related to U if and only if the difference is a member of W, then this relation tilde is an equivalence relation on V, and the equivalence class of each element V in capital V is given by the set of all elements of the form small v plus small w, where small w range over capital W. So this we can simply denote it as small v plus capital W. Now we consider these as elements, we consider a collection which we call as V mod W, or sometimes for convenience sakes we can also have it as V over W. Okay, so we have that to be the set of all elements of the form V plus W. Then this V mod W is a vector space over F under the operations. First one, V1 plus W addition. V1 plus W one member, V2 plus W another member. The sum of these two is defined as V1 plus V2 plus W, and scalar multiplication alpha into V1 plus W is alpha V1 plus W. Now this each element of V mod W is an equivalence class that already we have said, and it is actually a slice of V. Now we have in R2 we have W to be we consider a line through the origin. We know already that it's a subspace of R2. So when we consider W as this and V as R2, then V mod W, okay, will consist of elements of this form. We'll have to have small v plus capital W, where small v range over capital V. So if we consider 1 0 plus W or minus 1 0 ordered pair, minus 1 0 plus W. So all these will be lines as shown in the figure, and they all will be elements of V over W, and each element of V over W is a slice of R2. Now to prove that V mod W is a quotient space, first we see that V mod W is an abelian group under addition. So that can be easily established. So we now verify the axioms V1, V2, V3 and V4 in any vector space. So for that we consider two elements, alpha, beta in F and V1 plus W, V2 plus W in V mod W. So the first axiom is alpha V1 plus W plus V2 plus W should be equal to alpha V1 plus W plus alpha into V2 plus W. So we consider the LHS, that is this. Using the addition in V mod W, we have this step. Using addition in V mod W, we have this step. And using scalar multiplication in V mod W, we have this step. Next, we have capital V being a vector space. Using the first axiom V1, we have this step alpha V1 plus V2 to be alpha V1 plus alpha V2, and this W written as such. And using addition in V mod W, this step is written. Using scalar multiplication in V mod W, this step is written. Now for the second one, what we are trying to prove in this is alpha plus beta V1 plus W is alpha into V1 plus W plus beta into V1 plus W. So for that we consider this expression. Using scalar multiplication in V mod W, we have this step. And V being a vector space, using the second axiom, namely V2, we get this step. And using again the addition defined in V mod W, we can rewrite this as alpha V1 plus W plus beta V1 plus W. Again using scalar multiplication in V mod W, from this step we get this. So that is what we want actually. And for V3, what we are trying to prove is alpha into beta V1 plus W is alpha beta into V1 plus W. So for which we consider this expression, and this is using our scalar multiplication. We can have this as alpha beta V1. Here we are applying a scalar multiplication in V mod W. So we get this step. Once more we use scalar multiplication in V mod W, and this step comes. And using V3 in capital V, which is a vector space, we have this step. And using scalar multiplication in V mod W, this step comes. Next, last V4, it is 1 into V1 plus W. We have to show it as V1 plus W. So when we consider this using scalar multiplication, we have this. And using V4 in V, we get this step. So as all these axioms for V mod W to be a vector space being true, we conclude that V mod W is a vector space, and that's called quotient space.